Students, today we will discuss on TCP and UDP, these two transport layer protocols. TCP and UDP, both protocols are very important for our networking communication. Both works in the transport layer of the RSI model. Now, the basic difference between TCP and UDP is that TCP is connection oriented and reliable, and on the other hand, UDP is connectionless and not so reliable. So we will discuss on these protocols today. Okay, so let's start with TCP. Now we will see the different features of TCP. You will see the data frame structure. Data frames we call it segment actually. So we will see the segment TCP, the format of the TCP segment, and then we will see how TCP protocol handle the congestion, how it handle the error detection correction mechanisms, etc. And later on we will move to UDP. We will see what is the features of UDP and what is the frame structure of UDP and all that. So let's start with TCP. So I'm sharing my note with you. So the features of TCP, if we see the different features of TCP, the first feature is that is TCP is reliable protocol. Now why reliable? I have already told you that as TCP is a connection oriented protocol and it also provides error detection, error correction, this kind of mechanisms, so TCP is reliable protocol. So obviously when we are using TCP protocol in our communication, in our data communication, then that communication will be reliable communication. So in that sense, TCP is reliable. Next is TCP ensures that the data reaches intended destination in the same order it was sent. So no reordering is needed at the destination end if you use TCP. So that is also another very important feature of the TCP. Next is TCP is a connection oriented. As I told you, TCP is connection oriented. So what is the meaning of that? The meaning of that is TCP requires that connection between two remote points be established before sending the actual data. So that is basically you can find it in circuit switching mechanism as well. In the circuit switching mechanism, it's a connection oriented mechanism where the connection is established between the source and the destination, then data transmission begins. So that same thing you can think here also, but it's not like that TCP do not support packet switching mechanism. It can support in different way actually, not directly maybe. So it will we can study that in our further courses. So this is how TCP ensures the connection oriented property. Okay. Next is TCP provides error checking and error recovery mechanism. It's a end-to-end communication. TCP and it provides a end-to-end communication. Provides an end-to-end communication. Next is TCP provides flow control and quality of service. Now, when we are calling flow control, when I am saying flow control means how much data you can send before getting an acknowledgement from the receiver. So that is flow control. And what is quality of service? Now, quality of service depends on various things, primarily on jitter. Next is on delay, next is on bandwidth, and these things basically. So if you want to achieve quality of service, your jitter should be less, your delay should be less, your bandwidth should be high. So in that way you can assure quality of service. Okay. Next is the TCP operates in client server and point to point both mode. It can support both the modes. And next another very important feature is that TCP provides full duplex communication. That means sender and receiver both can communicate at the same time. So this is another very important feature of the TCP. Now the TCP header, if we see the structure of the TCP header segment, so basically it is a 32-bit in length, and it consists of various fields like source port address, destination port address, the sequence number of the data field, the sequence number, the acknowledgement number, the header length field. Some fields are reserved bits. Now there are some flag bits like urgent pointer, urgent acknowledgement, push, RS receipt, SYN bit, fin bit. Now the SYN and fin bit is used in connection establishment and connection release mechanism. So you will see that. Now there are some window size where the window size is decided. Then some checksum bit. Now some urgent pointer is set over here. Now some options, if some options are there, actually the header is minimum 20 bytes long and maximum 60 bytes long. Now without any option it is 20 bytes, with options it may be up to 60 bytes. So that's the thing is. And then the padding bits and all that, and then the actual data field. So this is the basic structure of the TCP header segment. Details are given in this note. Actually, you can see that the source port is 16 bits, destination port is again 16 bits, and sequence number is 32 bits, and then acknowledgement number is again 32 bits. Header length is 4 bits. Reserved is 6 bits. Now this reserved is this is used for future use and all set to 0 by default. Okay. Now flag. Now as I told you, flags, there are several flags like URG, that is urgent pointer field. It has significant data and should be processed. Next is acknowledgement. It indicates that acknowledgement field has significance. If acknowledgement is clear to 0, it indicates that packet does not contain any acknowledgement. That's very important. Next, PSH, that is when it is set, it's a request to the receiving station to push data. That is as soon as it comes to the receiving application without buffering it. Okay, so that is the thing. There will be no buffering, then and then it will be pushed. Next, reset the flags. Okay, so these are the things. Same is the I told you that you will use it in the data connection establishment and connection release purposes. Then fin is data. It will be used in the connection termination time. So that is the fin bit. Now the window size. Now very important is that the window size. Okay, the field is used for flow control between two stations, and it indicates the amount of buffer the receiver has allocated per segment. So window size is basically it may be, the term may be new though, especially those who have not gone through my flow control error control lecture. Now window size is basically here we decide how much data we can send before getting an acknowledgement from the receiver. So in that case, how much data frame will be there, that will be my window size. Okay, how much data frame can be sent at a time. It is not actually at a time. I mean, before getting an acknowledgement from the receiver. So that is basically flow control. That indicates flow control, and that is derived by window size. That is decided by the window size. Okay, so window size can be shrunk sometimes. You will see that based on your data connection efficiency or inefficiency. And next is checksum. Checksum is used in that is for the error detection, error correction mechanism. And next is urgent pointer. Now urgent pointer, it's also a very important thing, that like it points to the urgent data byte. If urgent flag is set to 1, okay, that will indicate it is urgent. Now there are options, different options could be there. Okay, so this is about the whole thing of TCP segment format. Okay, so this is the TCP segment format. It's very important from your exam purpose also, because sometimes this question comes when I write down the TCP segment format. So that's why I have included it here also in my lecture. Next is we will move to connection management. That is TCP connection management. Now TCP connection management can be done in 3 basic steps. One is connection establishment. Next is data transmission. Another is connection release. Now, if I come to the connection establishment, now connection establishment is itself is a 3-way handshaking mechanism. That means there are 3 things are involved. The first thing is like that. If it is, suppose it's a client and server. In this picture, I will explain it to you. So suppose there is a client machine and a server machine. And not necessarily it has to be a client and server, because you have seen that in feature that TCP can support client server as well as peer-to-peer, all the things. So client server. Now if client wants to send some data, so before starting the data, client has to send a SYN bit, that is a synchronization bit, to the server. Getting that synchronization bit, server will send another SYN bit and the acknowledgement of the SYN bit sent by the client machine. And then after getting the SYN bit from the server machine, client will send an acknowledgement to the server. So in that way, this is a three-way handshaking mechanism, and connection will be established between the client and server. Now the data transmission will begin. Data transmission will happen and all that. And after during the finishing of the data transmission, there will be 4 steps. The first step will be the initiator, that is in our case we are assuming that is the client. So client will send a field bit. Next, getting that field bit, server will send an acknowledgement bit. With that, server will send another field bit if server is ready to finish the communication, and then client will get sending another acknowledgement that to indicate that it has got the server's response. So in that way, connection will be released. So this is the 4-step connection termination process. So there are 3 mechanisms involved in the connection establishment, then connection data transmission, and then connection termination. Okay, so connection establishment, data transmission, connection termination. Now connection establishment is based on 3 steps, that is called 3-way handshaking mechanism, and connection termination is a 4-step method. So this is connection establishment and connection termination mechanism. Now the error control in TCP. Now error control in TCP, there are several techniques. The first technique is very plain and simple, that is checksum. Now checksum we have seen in error control mechanism. If you have not gone through it, you can go to my lecture. It is there in my channel. That is what is checksum mechanism. And next is acknowledgement. Now acknowledgement, you can understand that if I'm sending some data to the sender and the sender is not responding me, then I can understand there is some error. So in that, based on that, I can rectify I will resend my data and all that. So that is acknowledgement. Okay, acknowledgement mechanism. Next is retransmission. Again, after some time, if the sender is not receiving the acknowledgement, sender will resend the data. That is the retransmission in the basic way. So these are the 3 things: checksum, acknowledgement, and retransmission. So checksum is first and very preferred method in TCP, then acknowledgement, and then checksum. Okay, retransmission. Okay, and next is congestion control. Now congestion control mechanism in TCP, it is handled in 3 ways. One is slow start mechanism, another is additive increase mechanism, another is multiplicative decrease mechanism. So I want to share with you this thing. So basically, what is congestion control? Why congestion control is needed? Because congestion control is needed to either to prevent or to remove the congestion in the network. Okay. Now there are 3 mechanisms. First is slow start mechanism. Now in the slow start mechanism, in the picture you can see, at first the sender will send first segment, 1 segment, then it will wait for the acknowledgement. Acknowledgement will be received. After getting the acknowledgement, sender will send 2 segments. Okay, then sender will wait. It will receive 2 acknowledgement. After getting these 2 acknowledgement, now sender will send 4 segments at a time. 4 segments. Okay, so 4 segments will be sent to the receiver. When I'm saying at a time, that not means it is going at the same time. It is going one after another, but at a single chance. Okay, like that. So now receiver is again receiving the 4 acknowledgements, and after that sender will send 8 segments, then 16 segments. So sender is sending data, and it is increasing this. So we are calling it is increasing it step by step. So that's why we are calling it slow start method. So at first in the small graph you can see, at first sender is sending 1 data segment, next 2 data segment, next 4 data segment, next 8 data segments, next 10, 16. Then maybe 32, like that. Okay, this is the slow start mechanism. Next, another mechanism is additive increase. In the additive increase, after reaching the threshold, because there will be some threshold value, so that is, suppose the threshold value is 64. So after reaching the threshold, the increment will be by 1. Okay, so increment will be by 1. So after 1 acknowledgements, the congestion window size will be increased by 1. Then congestion window size will be increased by 2. Congestion window size means the number of data we are sending at a single step. Like here, congestion window size was, at first it is 1, after that it became 2, then it became 4, then it became 8. So like that. So after reaching the threshold value, suppose it is 64, then we will increment by 1, then next one, like that. Okay. So that is additive increase. And another method is known as multiplicative decrease. Now in the multiplicative decrement, if the congestion occurs, the congestion window size is decreased. Okay, here it is not increased, here it is decreased. If congestion occurs, the congestion window size is decreased. Suppose we are sending 16, or our congestion window size is 16. Now congestion has occurred, so we are decreasing it from 16 to maybe to 8. Okay, again. So in the reverse order. Previously in the slow start we are increasing. In the multiplicative decrease we are decreasing the window size. So congestion window size is decreased. The only way a sender can gauge that congestion has occurred is the need to retransmit a segment. Whenever there will be a retransmitter segment, we have to retransmit the data, then we can assume that there might be some congestion. Okay. Now retransmission is needed to recover a missing packet which is assumed to have been dropped by a router due to congestion. Now retransmission can occur in one of two cases: when the retransmission timer times out, or when the duplicate acknowledgements are received. So this is the basic thing about the TCP congestion control mechanism. So next we can move on. Another thing, this is very important term, that is known as silly window syndrome. The silly window syndrome, this thing happens in the TCP protocol actually. Silly window syndrome, what is that? This is again related to congestion control, that's why I have included it. So silly window syndrome is a problem in computer networking caused by poorly implemented TCP flow control basically. Okay. If a server with this problem is unable to process all incoming data, okay, it requires that its client reduce the amount of data they send at a time. Okay, it has to request its client to reduce the data. The window setting on a TCP packet. Now, if the server continues to be unable to process all incoming data, the window becomes smaller and smaller because server continues to enable this process to process all the data, then window will become smaller and smaller, and sometimes to the point that the data transmit is smaller than the packet header, and making data transmission extremely inefficient. Okay, the name of this problem is actually silly window, silly window problem. It is known as silly window syndrome. The value is so small, that's why it is known as silly actually. So what happens actually? Again, I'm trying to explain you that if a server with this problem, suppose server is not able to process all the data, so what it has to do, it will request that its client that to please reduce your data sending speed. So as a result, what will happen? That congestion window size will be decreased, because at the same time previously it was 16, now it will become 8, now it will become 4, now it may become 2, now it may become 1. So this is basically silly window syndrome. Okay. So the receiver not advertising here what we can do actually to avoid it. The receiver not advertising small windows. This is accomplished by not advertising a larger window until the window size can be increased by either one maximum segment size or by half of the remote host current window size. That can be another thing. The sender must not transmit data unless a packet is at least as large as maximum segment size, or maybe a packet with data which is half of the remote host window size may be sent, and like that. So these are some methods by which we can avoid this basically silly window syndrome. Okay. Another algorithm is known as Nagel algorithm. Okay, this thing. All of the output data may be sent, and there is no unacknowledged data, or the Nagel algorithm is disabled. So that is basically the silly window syndrome. We can avoid it. So this is very important. That's why I have included. Okay. So this is about TCP. This is all about TCP. You have to know all these things about TCP. Now let us come to the UDP. What is UDP? It's a very simple protocol. UDP protocol, very simple man it is. Where it is a very simple man. It only transmits data. It works in the transport layer also. But my question is, why we need UDP when we have a very reliable protocol like TCP at the transport layer? That's a I think this is a good question. Okay, so the answer is that sometimes we need weaker people also, because situation demands. So here the situation, like suppose we are sending some video data. Suppose we are sending some video data. We are sending some video streams, multimedia streams. In that case, if one or two frame has lost, there will be no problem. So in that scenario, you can use UDP, because UDP simply drops the packet and it continues. So that is basically the feature of the UDP. So it is written over here. You can see that UDP is used when acknowledgement of data does not hold any significance. Acknowledgement is not so important. Okay. Now UDP is good protocol for data flowing in one direction. When data is flowing in one direction, suppose from my end to your end, so UDP is very good. Next is UDP is simple and suitable for query-based communication. UDP is connectionless service. I have told you at the very beginning of the class. UDP does not provide congestion control mechanism. It do not provide these things. UDP does not guarantee order delivery of data, TCP provides. Okay, UDP is stateless. Now, what is the meaning of stateless? Meaning of stateless means it does not acknowledge the packets being sent and have been received. So these things, UDP in that way, UDP is stateless. And that is UDP is suitable protocol for streaming applications of such as multimedia streaming. Okay, so this is basically UDP. Now, if we see the structure of the, the header format of the UDP, so it is based on, it is 4-part. It has source port address, destination port address, the length of the header, and the checksum. So this is basically the UDP header, and so this is basically the entire length of the UDP packet. Actually, length means the actual it specifies the entire length of the UDP packet, including the header. Okay, so this is UDP. And the application of UDP, there are lots of applications in the domain name service. You can UDP is used in the simple network management protocol like SNMP. UDP is used. Trivial file transfer protocol, UDP is used. Routing information protocol, UDP is used. Okay. Now the difference between TCP and UDP is very obvious. Like at first, TCP is connection oriented, UDP is connectionless. TCP is reliable, UDP is not reliable. TCP provides extensive error checking. UDP has only the basic error checking. TCP in the TCP is comparatively slower. UDP is faster. Okay, retransmission of lost packet is possible in TCP but not in UDP. Now TCP has a 20 to 60 bytes variable length header. UDP has 8 byte fixed length header. Now TCP is heavyweight. UDP is lightweight. Okay, so these are the things. TCP does not support broadcasting. UDP supports broadcasting, which is very important feature of UDP. And advantages also. Now TCP is used by HTTP, HTTPS, FTP, SMTP, and Telnet. This kind of protocols. UDP is used by DNS, DHCP, TFTP, SNMP, RIP. This kind of. So this is the basic difference between TCP and UDP. In this lecture, another thing I want to include that is DNS, that is domain name system architecture. Okay. Now domain name is a symbolic string associated with an IP address. Now, IP address is IPv4 is 4 byte, IPv6 is it's a 128 bit. Okay. Now domain name is domain name and IPs are basically it is numerical converted into binary. So very hard to remember. Now domain name is a symbolic string associated with an IP address. There are several domain names available. Some of them are generic such as com, edu, gov, net, etc. While some country level domain names are like AU, IN, ZA, US, etc. So the meanings are given here. Com means commercial business, edu means education, gov means government agencies, inc means international entity, mil means US military basically, and net means networking organization, org means non-profit organization. So these are the things. Now the following table shows the country top level domain names like AU means Australia, IN means India, Chile, France, United States means US. These are the things. These are you can see on the screen. Now, if I say domain name space, now the domain name space refers a hierarchy in the internet naming structure, basically. Okay, this hierarchy has a multiple levels from 0 to 127. Now, with a root at the top, it is like a tree actually. The following diagram shows this thing. That is this thing. This is like a tree. Suppose this is the root node, then under the root these are the nodes, then under that these are the nodes, these are the leaf nodes basically here. So this indeed in this way it is there. Okay, now in the above diagram each subtree represents a domain. Okay, these are the domain. Each domain can be partitioned into subdomains and this can be further partitioned and so on. Okay, so this is the structure of the domain names. Now name server contains the DNS database. This database comprises of various names and their corresponding IP addresses. Since it is not possible for a single server to maintain the entire DNS database, therefore the information is distributed among many DNS servers. There are lots of DNS servers. So here in the server there is IP address name. This mapping is there. Now, hierarchy of server is same as hierarchy of names. Now the entire namespace is divided into the zones. Now zone is collection of nodes basically. These are the collection of nodes. This is one zone, this is another zone, like that. Under the main domain, the server maintains a database called zone file for every zone, right? So this is edu zone, this is Berkeley.edu zone, this is cs.berkeley.edu zone, like that. Okay, now if the domain is not further divided into subdomains, then the domain and zone refers to the same thing, right? It is obvious. Now the information about the nodes in the subdomain is stored in the servers at the lower levels. However, the original server keeps reference to these lower levels of servers. Types of the name servers, you can say root server, primary server, secondary server, like that. Root server is the top, primary server stores a file about its zone, secondary server transfers complete information about a zone from another server, which may be primary or secondary server. Okay, DNS, how it works, if you see, when we type suppose google.com into the browser, it asks the local DNS server for its IP address, right? Now here the local DNS is ISP end. Okay, it is an ISP, Internet Service Provider end. Now when the local DNS does not find the IP address of requested domain name, it forwards the request to root DNS server and again inquires about IP address of it. Now the root DNS server replies with the delegation that I do not know the IP address of www.google.com, but I know the IP address of DNS server. The local DNS server then asks the com DNS server that same question. It will be com DNS server, yes, com as it is .com, so com DNS server, the same question. The com DNS server replies the same thing, saying that it does not know the IP address of the www.google.com but knows the address of the www.google.com. Then the local DNS asks the google.com DNS server the same question. The google.com DNS server replies with IP address of the www.google.com. Now the local DNS sends the IP of the www.google.com to the computer that sends the request. So in that way it resolves. So this is the basic picture. This is the basic picture how DNS work. Okay. So this is about it. This is about today's lecture. Hope you have understood the thing. Thank you.